So today we have Professor Eli Yablonovitch here as the seminar speaker, and I'm honored to give a brief introduction. So I don't want to take up too much of Professor Yablonovich's time. He is really well known in the field of optoelectronics and very much in particular devices such as solar cells or photovoltaic cells. He introduced the 4n squared light trapping limit, which is certainly one that is well known to me, having taught a course in solar cells at the graduate level here at Princeton, and definitely featuring a number of his developments. So I'm very honored to be able to give an introduction here. Professor Yablonovitch also has featured highly in the photonics world, working in the area of photonic crystals, having coined that term, as well as more recent work in the area of plasmonics. So he has a very far-reaching impact over his long career. He is currently at the UC Berkeley since 2007, where he holds the James and Catherine Lau Chair in Engineering, and is the director of an NSF Center for Energy Efficient Electronics Science, to which I think we are going to hear some of the recent developments in his lecture entitled, "Can Optoelectronics Provide the Motive Power for Future Vehicles?" Professor Yablonovitch.
Thank you. I need a prop. Okay, thank you all for joining me here. And I will actually be talking about photovoltaics, but photovoltaics without the sun. So let's see if we can find a way to do that. Now, it all does start with photovoltaic cells. Let me show you a little picture I have here. If you had your preference, normally you would prefer to use gallium arsenide solar cells. And that is because they are the most efficient and just plain better than other types of solar cells. So I actually have some here. But these that I'm showing you are very expensive because they have to be space qualified, and so they go through like incredible amounts of testing, and so these are not the type of cells that are used terrestrially. So people are always saying, oh yeah, gallium arsenide, sure, but it's so expensive. And one of the things we discovered some time ago, as has only recently become practical, is that the gallium arsenide solar cells do not have to be expensive. For example, in electronics, the electronics usually sits on a semiconductor wafer, and only the top micron of the wafer is actually electronics. The rest of it is just mechanical support. This is also true for solar cells. And so if you can separate the active part, which is the top micron of a wafer, you could separate it from the rest of the wafer, then reuse the wafer. You don't have to pay for the wafer each time. Now, when they build these in space, they don't care. They just they have a new wafer each time, but certainly it doesn't have to be that way. So let me show you the method we use, and it's indicated on this slide. And what it is that famously in optoelectronics, there are two alloys. You know, everything in electronics that works is an accident of nature. And one of them is the accident that aluminum arsenide and gallium arsenide have the same lattice constant. And famously, this produces a double heterostructure, which is the basis of lasers and LEDs, but also it is the basis for solar cells. It should be, anyway. You can make a worse solar cell, but you should make a double heterostructure solar cell if you possibly can. Now, one of the things about this, of course, they gave a Nobel Prize for the double heterostructure to Herb Kroner about 15 years ago. And, but one of the things you know is that once you get the idea that you can use aluminum arsenide, so let's grow a very thin layer. Before we grow anything else of the active electronic device, let's grow a thin layer of aluminum arsenide just to get started. We're allowed to do that. It is the same lattice constant as the gallium arsenide substrate. Now, they're very similar materials, and so they work together very well. But there's one respect in which aluminum arsenide and gallium arsenide are very, very different, and that is in chemical selectivity. So I'll just give you the punchline. If you expose these two materials to acid, aluminum arsenide etches and gallium arsenide does not etch. Okay, so what you do is you come in with some acid, And it comes in and etches away the aluminum arsenide, so the acid goes in. It penetrates a macroscopic distance underneath. And now the active part, the top micron, which you needed for your active device, then floats off. And the substrate, which is about a half a millimeter thick or even thicker, can be reused. And so in this way, the cost goes down. Now, it just so happens I have some of these with me. So let me show you what happens when you have very thin gallium arsenide. Now, this was originally grown the way gallium arsenide is usually grown. It's grown on the wafer, perfectly lattice matched. And after you peeled it off, what happens, it comes out very flexible. It's still a single crystal, and it has great advantages. Now, this process was perfected. The commercialization of this was actually done in a company I founded. You'll hear more about the company in a minute. But one of the things that happened in the company that's very surprising is that they, of course, before they peeled it off, it was already a solar cell. And after they peeled it off, the voltage jumped. And I was on the board of directors, and so your voltage is what? And I said, whoa, I've never heard of such a high voltage. And then it just went on and on. So as soon as they peeled the film from the substrate, the voltage jumped to a record voltage. And the voltage kept getting higher and higher. So I'm going to describe a little bit about that and what it motivates us toward. So what about this selectivity? So this is actually also kind of interesting. See, I see a lot of young people here, but the older scientists, like myself, we didn't have the benefit of the internet. But we had something else. It was the Handbook of Chemistry and Physics. Okay. Now, the Handbook of Chemistry and Physics, it tells you the melting point, the color. It has a list of all the inorganic compounds, but then it has a cryptic column at the end. And unless you're an aficionado, you don't know what the column is, because all it says is I or S. And I see I'm getting some laughter, maybe from people who are in the know. Raise your hand if you know what the I or S means. Okay, Steve? Soluble and insoluble. So there's a tendency for things to be binary. Either they're soluble or they're insoluble. Now, every now and then you'll see SLS, which is slightly soluble. Nonetheless, that's sort of a remarkable property of nature, that it's either or. It's usually either or. So now you have gallium arsenide and aluminum arsenide, and it's either or. The gallium arsenide is not soluble, so it's I. And aluminum arsenide, even though these are very similar materials, same lattice content, but one of them is so different from the other. And we actually published a paper on this, and we said it was at least 100 million times selectivity in the solubility. It's actually probably even more than 100 million times. So because of that, you can peel the film, and this sort of comes out from a 6-inch wafer, and the acid comes in over a 2-hour period. The acid comes in from the edges, and this thing can be peeled right off. It's quite amazing. This is an earlier version of this. It was, I thought I had discovered it 30 years ago. It turns out some Japanese had actually published this about 10 years earlier, but there were various problems making it practical. This was during the era when they could only do 2 inches. But there are various ways of doing it. We don't do it this way, but they did it so they just put a single drop of acid here, and they kind of peeled it off that way. It's kind of remarkable. So this is the device. Essentially what I'm showing you here. It is actually the world's record solar cell, and so we're proud of that. And it was done by this company, which I'm a co-founder. My other co-founder is Harry Atwater. Maybe some of you recognize him. But last year, we sold the company to this gentleman, Li Huijun, or in English, David Li. And he is a Chinese billionaire, and his company is called Hanergy. So Hanergy bought Alta Devices. So I've been a little frustrated on the outside looking in for the past year, but he's kept the company going. They've made some progress, and you can buy these types of solar cells. They don't give them away. They used to give them away, and now you actually pay for them. So this is an idea, and you can see what one of the first applications might be. Here you have the wing of an unmanned aerial vehicle. This is me. back there, and these are flexibles. These solar cells, in addition to being the most efficient, are also happen to be flexible, lightweight for unmanned aerial vehicle, and potentially very low cost.
Who is this guy you met?
This is one of our venture capitalists. Okay, so have we identified everyone in the picture? This is the Chinese billionaire, Li Heizhuan.
And he only showed you.
Okay, all right. It just so happened it was a happy occasion when the company had lots of money, and we had a customer who was testing it on the unmanned aerial vehicle. Okay, so what happened with this? I gave you a little bit of a hint of what happened with this solar cells. Is that it started getting very high voltages. But curiously, the high voltage occurred only after the film was peeled from the substrate. And that's kind of strange. So to give you an idea of what was going on, from 1990, for 2 decades almost, the record was unchanged. I think this is mostly because there was no money going into the field. Okay? And then over a relatively brief period of time, the record jumped to 28.8%, where it now remains since 2011. Well, at least since 2012, maybe. The record has been 28.8%. Alta has owned the record since 2011 and has only broken its own record since that time. Okay, now what is the record due to? It's completely due to the voltage. So you see the people got a respectable voltage. These were the record solar cells as they existed over the same period of time. And what happened is the voltage of the solar cell jumped by 1/10 of a volt. Now, solar cell records are not supposed to be broken by a huge amount. You're not supposed to suddenly jump up in voltage. It's like the 4-minute mile. You get the next record is going to be 3 minutes, 59.9 seconds. Okay, so what business do we have jumping the voltage by 1/10 of a volt? So something new came in. And there was some new physics. So to give you an idea of where things stood about, let's say 5 years ago, is that the record was roughly 25% for both gallium arsenide and silicon. However, if you go back to Shockley, who wrote the theory, at a very brilliant theory, even though it's Shockley, it was still amazing, explaining the thermodynamics of solar cells in just an amazing way, but that works out to 33.5%. And so for the history of solar cells up until that time, they said, well, 25% is pretty close to 33.5, so we'll quit there. Okay. And yet there's this 8.5% going, and we ended up somewhere in the middle of this. So we got into the new physics. There is some new physics in the solar cell that gives you the higher voltage. So I'll try to explain the new physics. Oh, here it is on the next slide. So this is the physics that allows you to get a super high voltage. So this is the picture here at the top is what happens in a normal solar cell as described in textbooks. The sunlight comes in and you produce an electron in a hole and you collect the electron hole. And that's how the solar cell is supposed to work. But as of 5 years ago, the picture is changed. It's not in the textbooks yet, but here it is. The picture is quite different, and that is the sunlight comes in, produces electron-hole pair, which immediately recombine to produce a luminescent photon. The luminescent photon kind of bounces around internally, and sort of bounces, and then produces another electron-hole pair, but that also recombines and produces a luminescent photon. And then the luminescent photon, this is an infrared photon, bounces around, gets reabsorbed, re-emitted, reabsorbed, and finally produce an electron-hole pair that gets collected. And this building up of the internal infrared photon gas is essential toward achieving this extra 1/10 of a volt. I should mention, a 1/10 of a volt doesn't sound like much, but you have to remember that, for example, a silicon solar cell, the operating point is about 5/10 of a volt. So we're talking about a pretty big improvement. In any case, it also broke the world record. Let me show you something else that happens that has not been discussed very much.
So how do you directly prove that that is the mechanism?
I think it'll come out in context, but if you're not satisfied with the proof, ask me again toward the end. Okay. Another thing happens, and that is that sometimes you create this infrared photon gas, and sometimes those infrared photons escape Okay, and so the new physics of the solar cell is if you hope to achieve the close to the theoretical limit, it's not enough just to have an ordinary solar cell. What you have to allow for is the buildup of a very intense internal infrared photon gas. And that infrared photon gas, if you have one sun coming in, you might have to build up that photon gas to 30, 40, or 50 suns internally. And then you will start to approach the theoretical limits. So it says the theoretical limit, Shockley's theoretical limit, is compatible, in fact requires that there should be an internal photon gas that is up to 50 suns, even if there's only one sun coming in. So it's a bit surprising. It's one surprising thing. The other thing surprising is that it's going to turn out that this mechanism that is accompanied by losing some of the photons, that actually external emission of the photon is not a loss. It's actually required. In order to have a high-performance solar cell, it has to do extremely well at emitting light, which is totally counterintuitive because a solar cell is designed to absorb light. But it has to emit luminescent light, surprisingly. Now, of course, all of this was anticipated by Shockley. In fact, I have here an equation. By the way, I don't like to use equations, so I use an equation that usually fills the entire slide. Okay, and so Shockley had his theory, which said there's some kind of ideal voltage that you get out of a solar cell. Now, he didn't actually write down this equation, but this equation was written down a few years later by a graduate student at Berkeley by the name of R.T. Ross. He later on had a career in biophysics. And at that time at Berkeley, there was a guy called Melvin Calvin who had worked out the steps in photosynthesis. And he told the student, can you also figure out if this has anything to do with solar cells? So he read Shockley's paper, and he understood Shockley's paper very, very well, and went a step further. He said, yes, Shockley told us what is the ideal voltage, except that you get the ideal voltage if you have 100% external luminescence efficiency. Because what Shockley said was that if you're at open circuit and the electrons and holes have no place to go, ideally they would just come back at the sun. Okay? And the degree to which the photons do not come back to the sun, that is the degree to which you actually lose voltage. And so Ross, in the 1960s, late 1960s, he already wrote down this exact formula that says you will lose voltage according to the fact that you're not good at emitting light. So it's a very strange requirement that a great solar cell has to emit light, not just absorb light, it has to emit light. And indeed, it's the external, not the internal emission that matters, because you're kind of trying to bounce off the sunlight, which is coming in from the outside. So this is, for us, it's a very important formula, because it says, work really hard at getting your solar cell to be a great LED. Get it to emit light very, very well. Now, it's not that easy to get the solar cell to emit light any more than an LED. It's also very difficult to get LEDs to work well. 20 years ago, people were happy with a 2% efficient LED. And one of the reasons why they were happy, well, they didn't have much choice. If you look at the escape cone for light from an LED, it's pretty narrow. It occupies about 2% of 4 pi radians. And so 2% of light could escape very readily like this. But 98% of light would bounce around internally in the LED and just go on and on forever. So people were resigned to 2% efficient LEDs. And then they realized that, oh, that's no good. You got to get the light out. So they made special effort to get the light out. Now, the special effort, one of the things you can do, you can absorb and re-emit, and then you have another 2% chance of escaping. Or you can make one of the surfaces rough, various things. But all these things to get the light out require tremendous internal efficiency because you're going to make several attempts. It's not easy to get out. So you have to make several attempts. And so the internal efficiency needs to be very high. And in fact, it turns out that if you look at all the loss mechanisms, you need 99% internal efficiency just to get 50% external. So it's actually very hard to get light out. And people have spent many years perfecting LEDs. Now if you go to the hardware store, you can get an LED bulb with over 50% efficiency. But it's got a lot of this stuff built into it. So it's really hard to do. Yeah, 99% internal just to get 50% external. Ooh. It seems like a lot of work. So let me give you an idea how hard it is. And part of it is that On any attempt, only 2% escapes. If you have to make many attempts, you better be close to over 98% efficiency. So what happens if you, for example, look not at the luminescence efficiency internally, but rather the rear reflectivity, because it's also a mirror. You need a very good mirror, and because you're going to be reflecting many times. And here's a statement that 90% reflectivity is not enough. And here's sort of an example. You're obviously, if you make the rear mirror more reflective, it gets more and more efficient. But a lot of the improvement, it gets really steep, well above 90% reflectivity. So you don't get much of the benefit until you're well over 95% reflectivity. And the current is doing nothing while you're improving the reflectivity. The boost is entirely due to the voltage. So as you go 96, 97, 98% reflectivity, you get a tremendous boost in voltage. And so that's what happened at Alta Devices. And in fact, it's kind of interesting. I told them, test the luminescence efficiency. It's very easy to do that measurement. You just look at the light coming back at you. Test it, and only process the material that you've grown that has high luminescence efficiency. So you'll know in advance, is this going to be a record-breaking cell or not? So it saved them a huge amount of work, because they only processed the ones that were going to break the record. And so this is, this is the record result. It is still the record. It's about 3 years old now, and it's quite a respectable cell. And as I mentioned, it broke the earlier records by almost 4%. So it's because it had this new physics in it. And I think I mentioned the story is that what happened is that they started getting amazing voltages as soon as they peeled the film off. Now, why is that? Well, if this solar cell is sitting on a substrate, and this material is epi-gallium arsenide, this is epitaxial gold, this is the best semiconductor you can have, but it's sitting on a kind of ordinary, unimpressive substrate. So any light that goes downward, so what ended up happening, 98% of light would go down into the substrate, and you'd never see it again. And as soon as you peeled the film, suddenly that sink for infrared light went away, and you could build up this internal photon gas. And so what happened in the company is they had a 96% reflector, and they broke the world record. What's going on? So I said, improve your rear mirror. So they went to a 97% reflector, and they broke their own record. And then they went to a 98% reflector, and that is the current world record. Okay, so that's more or less the sequence. And also in parallel, I had a student, Owen Miller, who is now a postdoc at MIT, and his job was to do the modeling. And I said, Owen, show me the model again. And I said, oh, it was there all along. We didn't realize it. It was right there in the theoretical understanding. But one usually makes pretext, oh, why didn't I get to the world record? Well, or why didn't I get to the theoretical limit? There's always something, but actually it's this. It's specifically the inability to get light out. So there are two things you need to approach the world record, and one of them is you need a good material, so good internal luminescence yield, well over 90%, and you also need well over 90% for the mirror. And both of these are needed to achieve a record solar cell. So if you happen to have a solar cell that's 25% efficient, stop worrying about the electron-hole transport. That is all right. Now, unfortunately, most solar cell people are always thinking in terms of electron-hole transport. And I say, stop worrying about it. It's fine. If you plan to make any improvement above 25%, it's not about electron management. It's about photon management. It's about helping the photons to get out. And the mantra is a good solar cell has to be a good LED, and a great solar cell has to be a great LED. Now, the record solar cell is about a 40% efficient LED. Okay, so it's not that it can't be improved further, but it's actually quite amazingly good. But there's some...
You have temperature in that equation too. Does temperature not matter?
Well, there's a standard temperature at which the records are set, and it's I think it's 25 degrees centigrade. And by the way, nobody measures their own record. You have to send it to NREL or to some national lab, and if you're in a foreign country, you send it to their national lab, and they test it, and they tell you whether you broke the world record. Okay, So, and they have everything set, and there's certain rules you have to follow to be able to call it a record. It has to be at least a square centimeter in size, and the record is measured at a fixed temperature. Of course, it's a little bit unphysical because when you use the solar panel, it's sitting on the sun, does get warm. I'll tell you a little story about that in a minute. Right now, I want to point out that this is somewhat counterintuitive because everyone has always said the best solar cell is a wafer solar cell, and then a thin film cell is cheaper, but it's not as good. And that's the assumption. But as you can see here, these thin film cells are actually better than the best wafer cell. In fact, it did not achieve the record until it was peeled from the wafer. So that's counterintuitive to those people who have been steeped in the tradition of this field. Then the second thing that's extremely counterintuitive is why should a solar cell give any photons back? And it says give back some photons. It's not just charity, it's actually needed to achieve the world record. So what's with that? So it's so counterintuitive that the company put out a press release, and I was a busy guy, so I didn't look at the press release. And then I looked at it, and it said that the reason that the solar cell was performing better was that the photons were somehow being reused, and you had more current. And that, of course, was not the case. You had more voltage, not more current. So it's very hard to explain this idea that you're actually going to make the solar cell more efficient by giving away some photons. And so because it's so hard to explain, I had 5 explanations. But then it ended up getting, people were yawning during that part of the talk. So I'm going to give you my favorite explanation, but it may not be intuitive for you either. It is hard to explain, okay? So reason number 4 is that luminescence is voltage. Okay, now there's a formula, and this, you can just derive this from thermodynamics, is that luminescence is the Planck black body radiation multiplied by the internal voltage. There's everything that's excited has an internal voltage, even if it's not a semiconductor, even if it's a dye molecule, there's an internal chemical potential associated with the excess excited states. And so there's some kind of a voltage. And so that can be derived thermodynamically. So what it says is that, yes, sure, go for luminescence because that means you have more voltage. So, okay, but maybe that's not completely obvious. But to give an idea of what's going on is that people in the know, they will not bother with a voltmeter. They will just measure the luminescence. If you calibrate the luminescence carefully, and I've managed to convert everyone at Berkeley to do this. So they don't do IV measurements anymore. They do light in, light out measurements. And if you calibrate it, it's a contactless voltmeter. And so this is a statement that, yes, of course you want more luminescence because luminescence measures voltage. Now, to give an idea of the degree to which this is sort of accepted in the industry is that they will, as a quality control metric in a factory, they'll put out solar panels out in the field, and they'll take a snapshot with an infrared camera, and they should all glow in the infrared. And if they don't glow, you take that panel that should not be shipped. There's something wrong with that panel. And so they use it for quality control. And so this viewpoint is somewhat tautological. It's good luminescence, is good voltage, and therefore it's a good thing to have. But as I say, there's a bunch of other reasons, and they all amount to the same thing, though, is that you want luminescence. And it was anticipated in Shockley's paper, except he didn't quite write it in this form, but this was applied in Shockley's paper. You lose voltage to the extent that you fail to get 100% external luminescence efficiency at open circuit. So open circuit, the electrons and holes have no place to go, and if they go into heat, that's obviously bad. So if you get 100% of the light out, then that's good. So that's another way of explaining it. This can be made into a dual junction. Now the dual junction is with this gallium indium phosphide. It looks just the same as what I've just shown you. So it's flexible, it looks the same, you can't tell the difference, but it is a 2-junction solar cell. And that one, well, the company got up to 30.8%, but NREL using the same principle is over 31%. So this pleased the CEO. He said, give me any efficiency you want, except that it should start with a 3. Okay. Okay, so that exists. So let's talk about the so I just went over the physics of solar cells. You have very high performance as possible, low cost as possible. I claim this can be lower cost than any other kind of solar cell, and certainly lower cost than the silicon panels. Because largely, well, I'll give you my reason, is yes, this is gallium arsenide. It's 10 times more expensive than silicon, but use 100 times less material. Okay, so it's 10 times more expensive, use 100 times less. So that's the property of these thin film direct gap materials, is that you don't need very much, and so it ends up costing next to nothing. And this, I mean, it's like paper, and you can roll it up, and it's very easy to imagine covering large areas with it. But let's go into now what is the economic and social situation in the solar cell field. Germany is a country that had made, over 10 years ago, made a very big commitment to solar panels. Now, I can't get a straight answer. I've asked my German friends, was this to appease the Green Party so they would join the ruling coalition? And I think that was the case, but they won't give me a straight answer. So it was accepted dogma in German politics that they were going to subsidize solar panels, which they have done very successfully. And I have here some data, and by the way, they have now reached 40 gigawatts installed capacity, which is an amazingly large amount. 40 gigawatts, it's mind-boggling. It's huge, and if you travel through Germany, it's everywhere. Now, how much did they get? So this is a Saturday. I've chosen a day at the end of May. So solar cells are at their peak, not on June 21st. They're at their peak at the end of May, because solar cells are little thermodynamic engines, and they actually work a little bit better if they're cool, so a little bit cooler in May. So you get your peak output at the end of May and not at the end of June. Okay, so here was a day at the end of May, and between the solar and the wind, 50% of the energy was renewable on a Saturday. Now, why Saturday? Because there's less demand on the weekend, and so you could make a bigger impact. So that is a great achievement. So it's a phenomenal historical achievement. However, it came at a very high cost because Germany was buying these solar panels, subsidizing them at a time when the price of the panels was very high, and caused a silicon shortage, caused the price of silicon to shoot up by more than a factor 10. And so Germany has spent 10 to 11 euros to get there, which is 100 billion euros. And it looks pretty good because it's 50% at high noon on a weekend day in May. But even on that weekend day, it's this triangle of photovoltaic production versus that rectangle of the rest of the day. And so even on that day, which is the best day of the year, they only covered 20% of their needs with solar. Now, they couldn't go past 50% penetration because they would have had to turn off sources that do not cycle. So 50% penetration was it. It would be great if we could live with 50% penetration, but that was May. Flash forward 6 months into November. And in November, there's almost nothing produced by solar. So if you average over the year, the average was 50% at high noon in May, but average over the year, it's only 7% of its electricity was coming from solar. And the reason is that you need seasonal storage, and we don't have seasonal storage. So this is a problem. Nonetheless, the 40 gigawatts of installation, it's still an achievement, and why shouldn't every country do what Germany did? It's still 7%. And now the panel price has dropped tremendously due to a price war. And so why shouldn't every country do it? So this is a problem. And so this is what has now happened. Crystal silicon is still the king technology, which to me is very sad because it's an early 1950s technology. So it's kind of pathetic. The efficiency varies in production. There are better ones and worse ones. It has 90% market share. Because of overbuilding in China, they built too many factories in China. There is 70 gigawatts a year of worldwide production capacity. And in the past, the worldwide demand has been half that. They say now the demand is catching up. So this year, there might be a worldwide demand of 50 gigawatts, which means there's still overcapacity, and there's a price war. So as a result of the price war, the current world price has settled down to about 60 to 70 cents a watt. But there are huge factories in China that are idle because they can't cover their variable costs. So think of what it means to have a price of 60 to 70 cents a watt and some of the capacity is idle. What it means is the variable production cost before you paid for the capital equipment. The variable production cost is 60 or 70 cents. So if you throw in the capital equipment cost, probably these are not such a great thing. These are like $1 a watt if you add in the capital equipment cost. Now, this is really bad for researchers like myself for the following reason, is that they have idle capacity. Now, Germany is built out. Germany has 40 gigawatts, and they're maxed out. They're giving away the electricity in the summertime. So what if every country would do that? So I think I have a slide here. It shows, this one is very hard to see. It shows the installed capacity in 2014, 175 gigawatts a year. Then this year is supposed to be 230 gigawatts a year. Let me just go back. So what it means is that when we reach about 2 terawatts, the whole world will be like Germany. They will all have solar panels all over the place, and they will only be satisfying 7% of their electricity. And because these Chinese factories exist, they're not about to turn them into farms. So they're gonna be there overhanging the market, and there is enough existing capacity. This is 70 gigawatts a year of annual capacity. Over 20 years can satisfy the entire world's demand, so the entire world is like Germany. You don't need any new technology, you don't need any new factories. Okay? So this is a big problem to us researchers. So what I'm going to say, sort of this part, is to say, to justify any additional production capacity, new applications are needed. New application markets are needed, because this idea of supplementing utilities is sort of, it's done. It's too late. So I'm going to show you a new application that you can be the judge whether this can now be the new application while we wait for all that excess, all those panels to be built out, and every country becomes like Germany. Okay. And I have to tell you a little bit about how did we get into this pickle. And what happened, is from speaking to my Chinese friends, is roughly as follows. There was a lot of talk about solar, and they got wind of this in China. And every province in China, they all have unemployment problems just like we do here. And they said, we're going to become the world capital of solar cell production. Our province will become the world capital. Then the story goes, the central government, you know, there is some direction from the central government there. And they said, oh my God, every province thinks it's going to be the world capital. That can't be. They're building too many factories, too many plants. And so they put out an edict from Beijing that said, look, unless you have a world-scale plant, which is a gigawatt a year, we're going to have to shut you down. It's too small. You're too small to be economic. So what happened is very quickly every province built up to make sure they would reach a gigawatt a year of capacity. And so it was sort of an example of politics working out sort of backwards to what people had intended. So the counterintuitive consequences. So we need new applications, therefore. Okay, so here's a new application. And this was actually, it's not that new. It was first pointed out in 1960, is you could take something very hot and with a black body spectrum, and part of the black body spectrum, this part down here in the tail, the part of the black body spectrum is big photons that I can use to make electricity. Okay, and you can go at different temperatures, and it works out if you can make electricity. You take out maybe 5 or 10% of the big photons, and then you make electricity. And this was actually developed. So it has a name. It's called Thermo Photovoltaics. And in fact, people really got excited about this, and they made weird solar cells out of gallium antimonide, and they put them into a car. This is a demonstration in a car, but it's an old demonstration. It's almost 20 years old. And so what's the problem? It wasn't very efficient. You're only using a very small part of the black body spectrum. You've got to do something with the rest of the black body spectrum. So what did they try to do? They tried many different things, but I'm going to tell you what they should have done. Okay? And that is, they had all of these photons that were too small for the photovoltaic cell. And so one of the things they could do is they could recycle those photons and recycle them over and over again. They're not using them, so they might as well recycle them and maybe reflect them back onto the heat source, so you don't need as much fuel to keep the heat source hot. And so that's what should be done, is to recycle the unused photons. And because they weren't recycling them well, they didn't have very good efficiency, and 20% is the best that I've heard reported over about a 50-year period. And this research has been going on for 50 years, on and off, for an extended period of time. And in fact, there were many attempted solutions. For example, people tried to make the black body not black. What if it's black only above the band gap of a semiconductor? Then it doesn't produce a Planck spectrum, it just produces these photons that you want, and doesn't produce any of these other photons at all. And so they were trying to engineer spectral selectivity into the thing that was hot. And that's the main approach for 50 years. People have been trying to do that. A spectrally selective hot surface. And indeed, at MIT, they have been working on this for some time, trying very hard. And they have these photonic crystal things on top, structures, nanostructures, that are spectrally selective and would tend to emit the big photons. But there's a little problem. Is it has to be, this nanostructure has to sit at 1200 degrees centigrade for years. And so it can't stand it. I mean, it can't stand the heat, literally cannot stand the heat. So this is a problem. So all they've been doing for 50 years is trying to engineer the spectral selectivity. And they had various things. So they're trying to make a selective emitter. Then more recently, they want to put another photonic crystal in front of the solar cell to get more selectivity, maybe reflect some of those infrared rays. But all of these, they were missing the most obvious solution to the problem, which I'll sort of tell you what the most obvious solution is. Remember, we needed fantastic reflectivity to get the record voltage. So this fantastic reflectivity means, accidentally, it also reflects the infrared rays that weren't being used in thermophotovoltaics. So that is the obvious solution. Now, I thought that was a great idea, and I was patting myself on the back. Then I read more in the literature. It had already been patented. Okay, here's a patent from 1967 to do exactly that. Now, General Motors at that time owned some infrared detector company in Santa Barbara. I don't know, somehow General Motors got this patent. And what the patent says is just what I've described, is that put a reflector in the back of your solar cell. The virtue of that, what is the best selective reflector in the world? The band gap of a solar cell. It's totally transparent below and totally absorbing above. Okay, so that it's the world's best step function reflector. And so why not just use the solar cell? So I was puzzled by this, and of course we have this. We already knew that we needed a great reflectivity, get a great voltage, but that was to reflect band-edge luminescence. But the reflector reflects all wavelengths, and so it does a great job on the infrared wavelengths as well. And so here, this is an example of the reflectivity of the record-breaking solar cell. It's just a fantastic step function. Okay, it's about as good a step function as you're going to find. So this is rather remarkable. I said, well, this is an obvious idea. It was patented in 1967. But then I noticed, I was reading the old literature, R.J. Schwartz was a co-author of the early papers on thermophotovoltaics. Now, maybe none of you know who R.J. Schwartz is, but he used to be the dean of engineering at Purdue. And I had met him, and I remembered him. And so I called up my friends at Purdue. I need to talk to Dick Schwartz. Do you have a cell phone number? He says, he's retired. Yeah, I know, I need a cell phone number. So they gave me a cell phone number, and I call him up. And he has a very big family, had many children, and he's visiting grandchildren in Palo Alto by coincidence. Okay? And so he's willing to talk. So I say, look, Dick, you're a pioneer. You wrote these papers. Why was everyone trying to get a selective emissivity when they should have just been using the semiconductor band gap itself as the selective reflector? And by the way, the idea was already patented in 1967, and you were writing papers long after 1967. And he says, well, yeah. The problem was, back in those days, we could barely make a solar cell. And the solar cells didn't perform well, and don't even ask us to make a good reflector on the back of it. We could barely, so if you take an ordinary solar panel, you go out to the store and buy a solar panel and take the infrared reflectivity, there should be no absorption at all, which is below the band gap of silicon. Unfortunately, all the priority is given to making good ohmic contact, and none of the priority is given to making a good reflector. And so the reflectivity is only about 60%, which is not very interesting if you're trying to do something with all these infrared photons. You're going to recycle them many times. It's another one of those situations you need a reflectivity well over 90%. So that's why it hadn't been done before, is that they just, I don't know, it was very hard in those days to make a solar cell. So this is the way to envision this type of engine, if you want to call it an engine, and that you have some heated thing, and it's very thin, it gets very hot, and it's rectangular, and it's inside a rectangular box, and the inside of the rectangular box is coated with photovoltaic cells. I have to be careful not to call them solar cells, because they're not coming from the sun. They're working on heat radiation, on thermal radiation. And so this thing is yellow hot in the middle, and the solar cells on the outside are cooled, so you need cooling to keep them at room temperature, and they're facing the black body radiation. They're reflecting 90% of the black body radiation back to the heat source, using 10%, converting it to electricity. And then the photons are bouncing back and forth, and after 10 or 20 times of the photons bouncing back and forth, finally all of the energy, well, all of it, but as much as possible, is converted, because every time you rethermalize, you get the high energy photons back. So you rethermalize 10 or 20 times, and you end up being amazingly efficient at converting heat into electricity. Now, to understand what's going on, at 1200 degrees centigrade, the black body radiation is 28 watts per square centimeter, which is equivalent to 280 suns. So there's a lot of thermal radiation bouncing around. So it's a regime which we're not that familiar with, but one of the great truths is there's a lot of suns, and so the usual bugaboo in photovoltaics, which is the cost per unit area, you don't need a big area, because we're talking about 280 suns. You need an area more like a concentrator cell, and not like a flat panel cell, because there's all this thermal radiation bouncing around. This is a cross-section of the same thing, so I hope that this one's a bit more understandable. So you have the infrared photons bouncing back and forth, and so forth. And the photovoltaic cells have to be cooled. But this is like a normal heat engine. You have a hot side and a cold side, so that part's not surprising.
What's the source of heat for the engine?
So, okay, the source of heat can be any source of heat you like. I have some people at Berkeley who want to use radioactivity for the deep space probes. And so they will, because right now they're using thermoelectrics, which in no way approach the efficiency we can achieve here. So let me tell you what the efficiency could be. And it is completely dependent upon the reflectivity at the back of the solar cell. So I've combined all my parasitic losses into the effective reflectivity at the back of the solar cell. And so the efficiency, if you get above 96% reflectivity, the efficiency goes above 50%. So the efficiency tends to be between 50 and 55% efficiency. Now, if you burn fuel for the heat, which you can do, you would burn half the fuel. Okay, so you'd have half the emissions. So if you burn fuel, but you could use the sun for the heat. So there's many things you can use as heat sources, and as many kinds of fuel that you can use as well. Now, what about the furnace efficiency? Because this is heat to electricity, but then you have to, how efficient are you at creating heat? So I went to an organization in Chicago called the Gas Technology Institute. Who has ever heard of the Gas Technology Institute? So some of the old timers here have heard of it. It is the Bell Labs of the gas industry. They do the research for the gas utilities, and so they have people that are experts on combustion. I exchanged some ideas, and they explained to me how you get a very efficient furnace. You have to recover the heat, so they call that a recuperator. You have to recover the heat from the combustion products, but it's a bit more complicated than that, in that you also have to prevent carbon buildup, because it's going to be kind of a small, kind of little furnace thing. because you have to prevent carbon buildup. And so there's kind of a secret. Let's say you're burning methane, and this is your basic reaction. It's like that, but you produce from burning the methane carbon dioxide and water, but then you have to recycle the carbon dioxide and water to prevent carbon buildup. And in fact, this is the correct amount. And if you recycle enough of the combustion product, the presence of water vapor in with the fuel means that thermodynamic conditions are unfavorable for carbon deposition. So everybody knows in engines you get carbon deposits. So you can work around that. And that's a good thing, a good workaround. So, but you can make a 90% efficient furnace this way. And this is, they actually patented this, is a furnace with a recuperator and with the thermochemical, it converts the fuel internally. Okay, so there it is. It's over 50% efficient and therefore has half the emissions. So it's pretty good. And this is, by the way, not for the theoretical limit. This is for a solar cell of equal quality to what we have today, which is it's equal to the current record-breaking solar cell, but does not require the Shockley-Queisser limit. Okay, so we do have the car. What do you need in the car? So let me give you some perspective on what you need. So a car needs at least 50 kilowatts. Now 50 kilowatts you can do with a solar panel about this big. So 70 by 70 square centimeters. And you'd have like kind of a furnace things, and they would have to be about that size. And the reason it's not that big is because you do have hundreds of suns available at that temperature. You can do other things. So for the car, this is sort of a few slides telling you how big the thing would be. So for the car, it's 70 centimeters by 70 centimeters, kind of a flat thing like that. Okay, let's say you wanted something for the home. So there is a great interest these days in code generation for the home. And every big industrial company is working on a gadget that will take in natural gas and produce electricity so that put the electric utility out of business because you can generate the electricity using natural gas. So one of the applications then for home use, but most of them are it's like internal combustion engines or Stirling engines or various kinds of engines to do that. So gas turbines, whatever. Here, and the target is usually about 100 watts of electricity, and then it's 50% efficient, so you get 100 watts of hot water. Okay, and that's sort of the thing. Actually, I should go back to the car. The car does need a radiator, but the radiator could be half the size of today's radiators in cars because you're twice as efficient. Okay, so you still need a small radiator to keep the solar photovoltaic panels, to keep them cool. So just keep that in mind. So here's one where the waste heat is hot water, domestic hot water, and it's roughly 50% efficient. And the size, we put a dollar bill here just to show you how big it would be. You could generate 1,000 watts from something that is slightly bigger than a dollar bill in size. Okay, and this would be as cross-section of the same thing. A little chamber, a little bit bigger than a dollar bill. Okay, that would generate 1,000 watts of electricity and 1,000 watts of hot water. So here's another application, quadcopters. This is a very big application these days. They're all over the place. If you do it with a lithium battery, it's not bad. It lasts for 20 minutes. However, suppose you have an application where you need to stay in the air for very protracted periods of time. And so the amount of time you can stay in the air depends upon the energy density of the energy source. So lithium battery obviously has much less energy density than liquid fuel. So if you have a liquid fuel and you just burn it to make the heat, then the energy density is 50 times higher than a lithium battery. And so instead of lasting for 20 minutes, it would last for 16 hours. Actually last even longer because I haven't taken into account the fact that it gets lighter and lighter as you burn the fuel off. And by the way, this applies to your jet engines. So this same reasoning is roughly why your longest intercontinental flight tends to be around 16 hours. Is because it just depends, you know, on takeoff you have a huge amount of fuel, and it's just the energy density of that fuel. So there's another possible application. In this application, it would just be the size of a business card. You'd be producing about 100 watts in something the size of a business card. It's a little tiny thing. And then I mentioned the space application, which we already have some colleagues at Berkeley working on. And interestingly, if you have silicon carbide pellets embedded with plutonium, don't do this at home. They'll just self-heat to 1500 centigrade. And that's that would be suitable. And it's amazingly stable. It will be stable in vacuum at 1500 centigrade for long periods. So that's kind of amazing for that. So I'm working on this project with my colleague, my co-founder of Alta Devices, Harry Atwater, and we already have some of these narrow bandgap solar cells. Of course, you don't want to make them out of gallium artemonide. You make them out of indium gallium arsenide, and they're pretty good. These are pretty good solar cells. The open circuit voltage, about 400 millivolts, is very close to where you want to operate the thermophotovoltaics. So we think the solar cell is going to be there. And we're doing some experiments. I'll skip that. So I was super enthusiastic about a year ago, and then I found out about the fuel cell vehicles. Okay, so the fuel cells are our strongest competitor. They do require hydrogen, but they can also be around 50% efficient. Okay, and they have already had 20 years of intensive R&D, so that this is in my neighborhood, Alameda Transit, and here's your H2 fuel cell vehicle, and there's different vehicles coming out. There's a Toyota coming out this year, and you can apparently already get a Hyundai fuel cell. So there's competition. But you have to be the judge on which way this is going to go. They do require hydrogen. Hydrogen storage is a pain. You wouldn't want to park this indoors. So it's another alternative. So let me arrive at some conclusions. I had sort of different title. Optoelectronics, is there anything it cannot do? And so yes, it can provide electricity. The solar cell is, or the photovoltaic cell is a optoelectronic device. It can be used in automobiles, and so in a hybrid automobile, it would replace the internal combustion engine, which are in today's hybrids. It could be used for home electricity and hot water. It could be used for aviation. We have not established a limit. Obviously, it can be used for unmanned aerial vehicles, but it maybe can be manned smaller airplanes. I don't know. But what is the nice thing about this? If we just use it for cars, and there is a lot of change happening in the automobile industry these days. If you use it for cars, and if this becomes a way of charging up hybrid vehicles, then that market is 10 times bigger than the solar panel market. So that's pretty respectable. So in the middle of the talk I said, we're in trouble, there's overcapacity in China, so you have to look for a new market. So what I'm recommending is that the photovoltaic cells should be used for thermophotovoltaics. And then we don't have to wait 20 years for all those factories in China to eventually be replaced, but rather that we can look for a new application which is non-solar and yet can have a big impact on energy. So that's the moral. Thank you.
In order to use it for these applications, you have to reject the heat at temperatures higher than atmospheric temperature. So that means that you're going to have to get to, as you had, 80 degrees centigrade or something like that. Yeah. And so how does the performance affected by that? If you get up, for example, in space, yes, you have to reject the heat at much higher temperature. I have a slide. So that's a very good question. If you're running an automobile flat out, you'd have to use the radiator, and the radiator would rise up to about 80 or 90 degrees centigrade. So at 90 degrees centigrade, you lose about 4 or 5% in terms of efficiency. So most of the time when you're driving it, I think you'd get the 50%, but it would drop to about 45% if you were running flat out in very hot weather. Yeah. The curve that you used there, what temperature did you assume for that?
That one was no ambient temperature for the 20 degrees cell temperature. Okay, so we've repeated these curves at 90 degrees cell temperature, and the curves go kind of like this. Okay, so you lose about 4 or 5% efficiency, but that's a very good point that you made.
Hi, thanks for the talk. I was wondering if you could go over the slide about the luminescence as the contactless voltmeter. So you talked about efficient luminescence requiring a large quasi-Fermi level split. But when you have a large quasi-Fermi level split, that means you have a lot of photogenerated carriers still stuck in the cells. You're not really pulling out a lot of current.
So basically, you're saying that to get the high performance, not only do you need high photon density, which I'm claiming, but also you need a high carrier density. Is that what you said?
Yes.
Go on.
So if you maintain a large quasi-Fermi level split inside the cell, that means you're not pulling out enough carriers.
You're doing what to the carriers?
If you maintain a large quasi-Fermi level split inside a cell, then you're not pulling out as many carriers.
Well, you're not pulling out as many carriers.
Yeah.
That's right. But this is for every solar cell. You have the open circuit condition where you get the biggest voltage. And what happens is that you give up a few kT of voltage in order to give the carriers a reason to go into the wires. And so this problem is called the fill factor problem. How do you get a good fill factor? So you always have to give up, let's say, up to 4 kT of the voltage in order to raise the probability, let's say, to 99% probability. So it's actually statistical mechanics. You give up a little bit of free energy, but then you get the lion's share of the current. And you need that. So part of operating a solar cell, and this is true for any solar cell out in the field, is you have to optimize both the voltage and the current. Okay, so once you have a high voltage, then you give up 4 kT, and you get the current and the voltage. Okay, so that's the way you do it. So in a solar cell, in every solar panel or in every system, they have an inverter that converts the DC electricity to maybe another form of electricity, which is more useful. But actually, the inverter performs a second function. It hunts for that optimum spot where you have optimized the voltage and the current together. Okay? And so as a proxy for that, I've been using the open circuit voltage as a proxy. But you're quite right, is that in practice, you would want to back off a little bit from the open circuit point in order to give the electrons and holes a reason to go into the wires.
Okay, thanks.
Any insights on the life cycle footprints upstream in terms of manufacture, energy, materials, water, downstream as well in terms of cell reuse or material recycling?
Okay. So let me give you an idea of how these are made. These are grown by blowing the precursor gases, blowing them at the surface. Okay, and the growth is over after 1 minute. It takes 1 minute to grow a solar cell. This is why this is going to be cheaper than any other type of solar cell. It can grow in 1 minute. So it only stays hot for that very brief period of time. So this problem you have with silicon, where the energy payback time has been questionable in the past, it doesn't occur here. People ask me, well, what is your energy payback time? And I say, I don't know, maybe
5 minutes.
5 minutes, something like that. It's very, very fast. But there are other inputs, as you point out. You have to have, there are other consequences. So let me mention some of the other consequences. It uses gallium. Gallium is not the most common material in the world. It's also not the most rare material in the world, okay? And it has a certain price, and it's a few $100s a kilogram. Now, I did the following calculation. I made the assumption that the whole world is going to go over to this as supplying all of the energy for the whole world. Everything, the liquid fuels, everything would start with this, okay? But like all major transitions, it wouldn't happen instantly. It would maybe take 100 years to happen, okay? So I said, let's say it happens 1% every year. So we're going to have to build a certain number of panels like this that amount to 1% of the world's energy every year. Okay? And obviously, we're going to demand a certain amount of gallium to make this happen. So that increases the current demand for gallium. It increases it only about maybe 10 or 20%. And the reason is there's so little needed here. It's a thin film. And so very, very little gallium is needed. So it'll make a minor impact on today's gallium economy. It won't even make a major impact. there's that aspect. I mean, I'm trying to look for, ancillary impacts that I need to worry about, and I have great difficulty finding it. Oh, here's one. Arsenic. Arsenic. That's like lead salt solar cells, which is a term we're not allowed to use. Okay. But arsenic, I went to the gardening store when I lived here in New Jersey, and I bought some crabgrass killer. I bought a 60-pound bag of crabgrass, because I was a suburban guy, okay? 60-pound bag of crabgrass killer, 14% by weight, arsenic. Okay, so yeah, it's not that big an issue. You want one? I'm still looking for an issue, but this is for today's solar panels. You put solar panels on the roof, and the firemen will not fight the fire because they're afraid of getting electrocuted in that house, because there's electricity all over the house, and you can't really turn the electricity off. You turn it off at the central mains, but the electricity is still up there. So I don't have an answer for that one exactly, but that is an existing known issue for solar panels, is that the firemen are kind of reluctant to work around the solar panels. But all of the things that you think of, I started in this, and I considered many alternatives. I started in this many years ago, like maybe 36 years ago, I started working on solar cells. And I've had, over that time, I had a chance to consider all of these secondary effects, and I've worried about them all. And this one, to me, seems to have the least number of problems, and the one that is most likely going to take us into the future. Because one of the things we need in the future, we have to create fuel because of the storage issue. Remember I said that Germany had a problem? So how do you do storage from summer to winter? There are not very many ways to do that. A battery is not going to be helpful going from summer to winter. And so you need fuel, and fuel has many other uses. Fuel is becoming more and more valuable. And unfortunately, though, to create fuel, today's depressed price of the solar panels, which is depressed by the price war, which is ongoing, we need to be a factor of 3 lower in price than today's already depressed price. And so we need something that can be super efficient and cost next to nothing. And I claim that society's diversion into subsidizing silicon solar panels has actually held back progress. That the subsidies have held back progress because, like all subsidies, they go to the politically influential. And that's the existing industry. So they subsidize the outdated industry. And in the meantime, it's creating barriers for new technology that would come along that would produce electricity so cheaply that we could use it to make fuel. So that's a bit of an editorial, I apologize.
So your last question.
Yeah.
How does the efficiency scale with cell area? The
yes.
maximum efficiency is on a 1 square centimeter
Yeah.
cell. How
That's
does
right.
it on 100 square
Okay, so they have so first they did the record on the square centimeter, because NREL would accept that for the record cell. Then they built a panel, and they sent the panel. So the panel was 1,000 square centimeters, and it was about 24.5% efficient, which is also a record for a panel. And to give you an idea, in production, they have over 90% yield of 25% efficient cells. So being crystalline, you don't have this drop-off of efficiency that you get with some of the polycrystalline materials. It's an ideal crystal material. So when you scale to a panel, it works almost as well as the individual cell.
On that note, let's thank Professor Yablonovitch again.